I have not yet started the recording, so let me start. Okay, good morning one and all. So in today's session, we will start with a topic called binary search tree, which is the continuation of the binary trees. And before we start binary search tree, we'll just discuss few topics like the disadvantages of a binary tree and what are the time complexities it is taking for certain operations, right? Once we just discuss that, recap that, and just we'll start with BSTs. What is none other than binary search tree. So binary search. I'm requesting once again people to please check the audio at their end uh, because a few people are saying they have an audio issue. So I hope majority have said the audio is good. So please do once check, and still you are patient with your audio jobs. Let me know so that I can talk to someone to get that fixed. Right? Okay. Okay. Great. So I'm sorry. So let me start the session. The question and answers such as the textbook and these we'll just talk at the end here. So let's focus on the questions that are related to the slides, and then we will discuss the generic discussion at the end, right? Okay. Right. Okay. Let me start. Okay, so as I have mentioned, today's topic will be having on binary search. Before moving into binary search, I will pose certain questions to you regarding the last session, which I expect you guys to answer me back. If not, also that's fine. But there are certain questions which I expect you to answer. Okay, in binary tree, which we covered in the last session, I think you have seen how a binary tree looks, which means to say that every node degree would be 2 at max, which includes either 0 child, 1 child, or 2 childs, which says that at max every node can have 2 childs, right? That was what we discussed as the degree of the node. Okay, and then when we were discussing this thing, there was any appropriate conditions, there were no appropriate conditions that were imposed on the left child or right child, right? So because of this, we have seen a tendency in binary trees as left skew tree or a right skew tree. This can happen, and we have also seen certain things called a full binary tree, complete binary tree, and certain things called a strict binary, which are not important for us at this instance. Now, when I talk about a binary tree, majorly I told this as balanced binary tree also, but we just are focusing on binary tree anyhow. Now, just when we are talking about this for instance, I have to do certain operations on the tree. The major operation that anyone would be interested in a data structure: insertion of data, searching of the data, and deletion of the data. Now, when coming to this situation, I would prefer my time complexity. I would prefer for my time complexity to be as minimal as possible. But can anyone say what is the time complexity of an insertion of an element in a binary tree? Insertion. So my question is, so I have got, okay, I can generalize your answers into two categories. Someone has, or three answers I have got which are common. Someone has said order of n, someone has said order of 1, and someone has said order of log n. These are the three answers I have got. See, order of log n may not be an appropriate answer because when we are talking, we prefer to always talk in sense of worst case scenario, right? Or in the best case scenario. So in worst case, what happens is the time complexity for the insertion of element is always order of 1, not order of n or order of log. Just give me a second, I'll discuss about it. When you decide a binary tree, see, just binary tree I'm talking. What happens is you just insert always the element on the leaf node. That's all. So you know where is the end in your array, just you insert the next element at the end of the array. The reason why is there are no conditions. What are conditions? For example, just let me quickly show you something like a binary tree. If you look this as a binary tree, you are able to see this as a binary tree. Do you agree? Yeah. Now the insertion can be happen at 2, 5, or 9. Anyone, that's fine. Technically, insertion will happen at either 5 or will either at 2. That's the reason in the leaf node only insertion happens. That's why people say order of 1. But when conditions are imposed, then the time complexity that we will see in today's session, right? Okay. Now my next question is, what is the time complexity of searching an element in a binary tree? I think if you see the slide, you get the answer. That is order of. Why? Because you don't know in where the element is present. You have to search all your left subtree or all your right subtree. Or else if it is skew tree, you have to search all the way in the left subtree or the right subtree depending upon what kind of skew. There is a good question. Someone says, if I have got a binary tree, if it is sorted, see what happens is, in that case, the in-order traversal helps us. If you travel in order on any full binary tree, your outcome is always sorted and you can find it in log n time. But the condition is the traversal should happen in order and the tree should be full. So there are two conditions where that's why it becomes order of log n. If you're coming up across order of log n, there is a condition always. It says the tree is a full and as well as the traversal we are using is in order. Please do remember it. But when we are trying to answer generically, let the answer be generic, right? Got it? That's the reason why it is order of 1. Okay. Even for search I'm talking, it's order of log n. The worst case search time here for a tree where it's just a binary tree, then it is order of n, right? Got it. Now, are you happy to perform some task in order of n and some task deletion also might take order of n? Okay, sorry. So let's stop. So if we have seen three operations on a binary tree. One is insertion, search, and deletion. Whereas search is the one which is taking order of n, whereas the deletion is taking order of n, but except insertion order of n. Are you happy to use such kind of data structure where the time complexity for search and deletion are taking more? Will you be happy for using such kind of data structure only for insertion? If you are only saying I'm going to use my data as archive, then it's a different story, right? If you are using, but after storing the data, you want to retrieve it as much fast as possible, which is not going to happen. Now, then what people have decided is, let's put something like conditions on a binary tree such that the search operation is happening very fast. Why? Because the search operation, what we have seen is order of n as the worst case complex, and best if it is a balance and we do in order, it is order of log n. Right? Got it. If you have a sorted list, you can say I will search from the first half or I'll search the second half. So some people have decided, right, good. See, deletion can take order of 1 if you are deleting the leaf node. If you are deleting the leaf node, it is order of 1. But deletion of an intermediate element, so you should definitely reach to that element and delete it. That's why I cannot say order of 1. I say order of n. Okay, deletion of leaf node or the last deletion of the last inserted value is order of 1. Always got that difference? What your answer is correct. Order of 1 is correct with respect to best case. But to search and delete an intermediate node, then there is issues arises. Got it? Okay. Okay. Now let's say using a binary tree itself, order of log n can be achieved for search condition. How is it possible? Assume that your binary tree is full binary tree and you're traveling in order. When you print in order traversal, all your elements that you get are sorted, right? Do you agree with that? Just if you want, you can try with a simple example. How do in order travel? Left, root, right. So right, so let's say 1, 2, 3. So it's basically it is always printing in an order. Right? When you have this order of elements, search can be done in order of log n time. Do you agree with that or not? See, you have been given a list of elements in array, starting from 1 to 10. Let's assume 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now, in this, if you have to search element number 10, you can do that because you will not search overall your array value. You know that A of 9 will have 10 and you can do. Swapna, I'm really sorry, voice, there might be issue at your end. Please check with your internet here, because majority of people have said they have voice clarity, because I can see only 3 people have issue with the voice breakage. Right? I'm sorry that, but if so, that's the reason why I cannot ask my tech team to help me here. Right? I'm sorry. Okay, let me try to finish this. And voice is breaking. Let me increase the. Okay, I think I'm sorry. I was at the lower from my. Now I think. Uh, now let me give 5 more minutes. See, I'm sorry. I just reduced my volume. I just increased it. If it is still continuing, please let me know and stop the video at least. Okay, right. Okay. Now that's the reason why order of login happens, but that's not always necessarily to be a condition. So that's why I said worst case is order of n. Okay, got it. Now I will be not happy to use a data structure where its time complexity of order of n. But if I am able to improve using the binary tree concept to order of log n in its worst case, I'll be happy. So what people have decided is, okay, let's impose conditions. See, this is all what I have written theory, so I'll just try to explain with the help of diagram directly here. What people have decided is, let's put some condition. In a binary tree, what it says, I will have a left child, I will have a right child, right? From my root node. This is a simple structure. If I try to store all the elements that are smaller than the root value on the left subchain and all the values that are greater than the root on the right subchain, I will know from which direction to travel, and my search time can be reduced. And this is a tree which we call it as a binary search tree. The search is major operation that is going to happen on the binary tree with imposition of conditions. What is the condition we are imposing? If I have got element, let's say 1. Now, the next element what I encounter, let's say it be 2. I am going to store the element 2 on the right side of the root node. And let's say I've got some element called 0. Where I'm going to store? I'm going to store it on the left side of the root node. This is what the condition we are going to impose. See, Purvi, you have a valid question. So one of your friend asked, let's say I've got only one node, and when I add another node, my time taken is order of 1. Yes, that's what I told you. For adding a child node to the binary tree is always 1, because I try to always add the child node to the leaf node. Okay, that's the reason why we have order of 1. That's the correct Purvi. What you said is correct. Right? In any case, even if the tree is full also, we'll try to add it at the first leaf node or second leaf node, and where it is order of 1. So that's why I told you, insertion is always order. See, textual value, no. BSTs are mostly we perform on numeric values. Even if you want to do text values, they do, but it is conversion of text to ASCII, and according to ASCII hierarchy, they do it here. It is possible, but it's a tedious process at this point. At this point, we don't need to discuss about the text process. Our whole agenda of the DST is to understand first how we can store data where the data is in numeric kind of format in easier way, right? Okay. Now you understand, if in a binary tree, if you're imposing a condition of storing all the smaller nodes than the root to the left side or the left subtree, and all the greater values than the root to the right, then we call it as a binary search tree. See, you have a binary search tree, we will not say it is balanced always. For example, I'll give you an example here. Let's look at this. I have elements 1, 2, 3, 4. Design me a binary search tree for this and say what is your outcome. Yeah, today I forgot to say you need to have pen and paper, because when we move to AVL, there will be a lot of work that you have to do on pen and paper. So please do grab a pen and paper when we start with AVL. Now, even for this, I just want you to just quick example and say me what is the kind of tree that you are getting. So I'm repeating the example that you want. You have to design a binary search tree where the values are 1, 2, 3, 4. Now say me what is the kind of tree that it is generating. So what is the condition that you are imposing? The first element is 1, the second element is 2, which is greater than 1, should be on the right side. So you put it on the right side. 3 is greater than 2, and 4 is greater than 3. So just design your binary search tree, which will be a right skew tree, right? So when it is becoming a right skew tree, can I say it as a balanced tree? Can I say it as balanced? So that's why binary search trees are not necessary to be a balanced tree. Okay, and it's a valid binary search tree. It's a valid binary search tree, but problem we have is with the time complexity. Don't worry, which we'll talk a little bit later. Okay, if the trees are skewed, we have issue, but assuming even that, so that is the case where you can encounter order of n in binary search tree also. Okay, that is a way ahead answer which I should. No, Ray, I did not say it has a balanced tree. That's why it is not necessary. Always a binary search tree should be a balanced tree. Okay, got that? It's not necessary. Even if you take two nodes, let's say 1, 2, I am missing the left chain. If you take 2, 1, I am missing the right chain. Got that? If you had equal number, that's one of the cases. Okay, how many people have tested? How many people have actually tested? In your test case, testing, just a simple testing of anything, any product. See, when you do some test, you use one of the scenario. The one of the scenario is a right skew, left skew. That's what I'm trying to say. It's something like the scenarios. Okay. Now let's go to some example. When you write a program, you give input value. So all necessarily, always all inputs need not be seen. So similarly, in a binary search tree, all keys may not necessarily to be balanced binary trees. That's what I'm trying to say. So one of the case you can get is a balanced binary. In one case, you might get a full tree. Sometimes you get a left skew tree or right skew tree. Okay, but condition, the only condition what I check is the element that is being stored as chain should be either greater. If it is greater, it should be right chain. If it is smaller than the root or parent node, should be on the left chain. Got it. Now I expect people to give me one answer to this. Let's say I have got 2, 2. These are just two nodes. Which will act as parent and which will act as the chain? If the second is acting as chain, where should I say? That is user defined condition. Any side is a vague answer. People have given right or left. The precise is always left here. Precise is always left. Because if people have the freedom to choose on right also, but they have to give condition greater than less than, but not again at one point right and one point left. No, at any one time, make sure you are giving the clear condition, either it is left side or right side, preferably always values less than or equal to root are stored on the left. If you want to put on right, you have the freedom, but make sure this condition is true throughout the tree, not at something like at level 1, I will do this condition, level 2 some other condition, which means greater than or less than, right? That's what I'm trying to say. Okay, so I have one second, last lecture. There was a point which you said that in order is not possible. Okay, so Swastik, that was the case when we had a chain where the degree of the node was 3, the leaf chain. So that we will discuss at the end, Swastik. Just remind me before we close the session. Fine. Okay. Now I think you are clear with the conditions. See, in real time, your BSTs are done mostly a job arrival, sequential of job arrival. Okay, so BSTs are done in the schedulers, BSTs are done in priority queues, but not as such BSTs. There will be different improvisation of BST. That's what we'll see with AVL. Then we will see with one more thing in the next section where we'll talk about heap sort. So these all are tree based. So improvements we keep on. So right. So in this example, say what are binary trees and what are not binary trees. Sorry. Let me go. Which one do you find? Which one? So this is A tree and this is B tree. Which one do you say are BST and which is not BST? So A is BST and B is not the BST. Okay. Why do you say B is not BST? Let's look at subtree 627. This subtree is holding BST property, yes or no? This 627, yes. But you are still saying why? Because every branch at the root, if you see 3 I have. On the right subtree, I'm finding 2. Technically, 2 should not be on the right side. 3, which are dotted. So that's the reason why the B tree is not a binary search tree. Okay. Now that's what you got satisfied with what is binary search tree. Okay. Now what are the operations that we generally do in binary search tree, and let's see what are the time complexity. In binary search tree, as I had told, always you find the maximum element, minimum element, apart from finding an element. Finding element is an element that is intermediately present. Finding the maximum element, finding the min element, these are certain operations. Apart from this, insertion and deletion. These are the basic 3 operations where finding we can subclassify as finding the max and finding the min. Why did I have discussed? Just let's talk. I just give you a random example for easier understanding of this. Just take this example. I'm just giving for the tree. I'm not talking about finding how you are going to find the min of 1. I hope you are clear with this tree. It is a tree where the values are segregated left and right. Got it? Just look at this for an easier example. Child of root. Follow me. I am not able to understand what means all the child of root node should be greater. Okay. Okay. Sorry. Again, I am repeating. If people have Harsha, you have a question. As per your question, I understand the second tree is a binary tree, but not binary search tree. Okay, binary search tree, we have a condition. All the elements on the left subchain should be smaller than the root node, and all the elements greater than all the greater elements of the root node should be on the right subtree. Okay, that is what is the basic condition. I hope this tree is clear for you. If you have copied it, we'll go back and have the discussion of find max and find min. Yeah. Okay. So let's go back for a minute, and then we will see what is that we were working on, finding an element and finding the maximum and minimum. Now, there is the least minimum element present in a binary search. Can anyone make a quick guess? The leftmost leaf node. The leftmost. Naveen, I could see you have raised your hand. Can you just post your question so that I'll be able to answer if there is a question. Okay. Once again, I'm going to the diagram. Okay, this diagram we can take. This diagram also is fine. This is also perfect. Okay. So by looking at in your tree, if you see the smallest element is present always in the left leaf node. So finding min element is pretty easy for me. First I should see whether there is an first I should see if there is a left node, that's a left chain node. I'll only travel on the left to left chain node. So what is the time complexity of identifying the minimal element in a binary search tree? Why order of log n or order of 1? No, not order of n. Order of n we will keep aside, assuming that's a left skew tree. The answer is, some people have said order of n, which holds when the tree is left skew tree. Now it is order of log n or order of 1. Give a try. That's a difference. Give a try. This is finding the minimum element. I think I've shown you the answer. Order of log and why I told you. Assuming your tree is a left skew. That's always you should say that. See, order of log n is correct. I told you today's session you will give me a lot of wrong answers because you understood the subject correct. Don't worry. Log n, your answer is correct because you are still in an assumption. A binary search tree is always a complete or a full binary search tree. That's what. Right? You got? Okay, you got the reason why you are getting log n. Why are you writing it as order of log n? I'll just say. What happens is when you are saying log n, you assume a tree. Okay, can I draw just a tree for a minute so that it will be pretty clear? Okay, let me draw a tree. Yeah. The diagram might be bad, but I try to do it in a better. One. 2, 3, 4, 5, 6, and 7. Okay, is this tree visible for you clearly? Yeah. Now what you said, first I'm discussing with the answer log n, why people assumed it to log n, and what the reason why, sorry, order of log n, why I'm not agreeing with order of log n, we'll just discuss it. No, I just did for easier to label here so that I have the balancing done clearly, okay? Since in a BST we travel only one left of the tree. Yeah, no, just that's what Rajesh, I'll just explain why it is order of n, why not order of log n with two examples. Now, by looking at this, people will quickly say order of 1 should be correct, okay, assuming I am traveling first with the leaf node when I do in order travel search. Technically, remember in binary search tree, most travel search are preferred with BS. Left, okay, then right, then root. Sorry, in order is also an option, but most of the BST says first visit the left, then right, and then the root. So remember, so just recollect what was this order all. Okay, so don't worry for this instant, but we decided to travel. People would have said, okay, I'm sorry, I'm confusing with you too many topics. Let's focus on why it is order of 1 and why it is not order of 1 and why it is not order of log n. Okay, and what made you to answer that, we'll have a discussion. Okay, now look at this. Is this a balanced tree? Would you agree first that it's a balanced tree, balanced binary tree? Yes. Is it a BST first? Yes, that also is a correct answer. Now let's see. The one who told order of 1, they assume that they will start with the leaf left node. So once they say that the first leaf left node, if I travel, if my start of travel happens, it starts with order of 1. That's the reason which they would have given as the order of 1. But we assume the travel would have been also happened at top to bottom. The people who assume top to bottom travel, sir, they said, I'm not going to travel full tree. Yes, they said they will be only traveling to the half side. Okay, half side. And the one who traveled order of 1 will be only true when they are saying, always I'll travel from the left, sorry, always I'll travel from this. But their answer will change for finding max. So just 1 second. This can't be BS directions. 5 is to be the right of the root node. Correct. Okay. You have a good question. 5 is greater than 4. Where it is on the right subtree. This whole is my right subtree, right? Is this correct? Okay. And then in 6 it is less than 6. That's why it is on the left side. That has to be iterative. That's why it is a valid BST. Okay. Now those who made the assumption of traveling half tree, they would have given the case of order of log n because they are traveling only half of the tree. In these cases, your both answers of order log n and order 1 was correct. Now let me come up with one more example. Where I'll disprove your half only, no. So here you will travel n by 2. Okay, here you are not traveling all the nodes. Again here it is n by 4 till you find it is so on till 1. So you are traveling, do the recursive operation. So that's why it is order of log n. Right, but easier thing I just understood. I made you understand. See, Soumya, I'll just draw your diagram in a minute. Let me explain why it is order of n. Then we'll talk here. Okay. Now let's because you just finished the half of the tree. So let's take an example for this. Sorry, this is not 3. 1, 2, 3. Now say, where is the minimal element and what is the time complexity if you are traveling from top to bottom? Got it? Why it is order of n? Because if this tree is left skewed tree. Got it? That's why. So you should always talk about the worst case scenario. N by 2, if you are, see, that's a recursive process. First time n by 2, next time n by 4, n by 8, n by so on till you find the element. That's why you say order of log. Got it? Okay. Do you want me to explain why it is order of n? See, it is order of n if there is a tree which is left skew tree. A left skew tree can be called as a binary search tree. Will you call this as a binary search tree or not? This example. Will you call this as a binary search tree or yes? Why? Because it is satisfying the binary search tree kind. And in this, what will be the time complex to find the minimum element is you have to start from top and you will keep on going and then you will say I am traveling all the nodes, that's why it is order of n. See, I told you why you consider order of 1, that is best case scenario. Got it? That's a best case scenario where it is order of 1. Got that? Order of 1 is not wrong yet. It's a best case. Order of log n is an average case and worst case is order of n. My question was order of worst case. Got it? Okay. Okay. Please binary tree yes, but not balance. See, balancing is a different concept. I am not introduced. Please do not get into that here. That is an AVL concept that I will discuss at the end. Now you understood finding. So by this time you should have understood what will be the time complexity to find an element which will be order of n. Finding a maximum element is also order of n. No, in order is not a necessary condition here. It's a tree travel. So someone can say I would not use in order. I will use pre-order or post-order. Someone can say I would use a level order. So we cannot impose those conditions. That's an individual way to travel. Now I have a question for you. Space because all the elements have to be stored. No, if I got n elements, I need a space of n. That's why it is order of n. Got it? All the elements I cannot store. If I got 20 elements, I need a space array of 20. That's why how many elements I am taking, that much space I need. That's why the space is always order of n. Got it? Got my two answers? Abhishek, you just let me answer that. In array, what is the space difference? Each element take one memory bit. So I have got n. So definitely my space is order of n even in array. Stacks are none other than simple way of implementation using an array. Okay. So I hope you understood the concept of finding the minimum, maximum and finding an element. Okay. You wanted me to, okay. Here can be the worst case scenario. 1 second. Someone had a valid question. No, 0, 1 is a best case scenario here. It's not worst. 0 order of 1 is always best case. It's not the worst case. Why? Because let's say you have got a root node itself. There is no left hand substitute. So you got the answer order of 1. Got it? That's a best case. Worst case is order of n. Got that? For finding the minimal element, maximum element and an element, the worst case time complexity is order of n. Got that now? Okay. Now I hope I'm clear with the time complexity of a binary search tree, why it is order of n, because there is no condition of balancing a binary search tree. There is no balancing condition here. Only condition we have is the element left subtree should have smaller element than the root and the elements that are greater than the root should be on the right subtree. That's all. That is all. Okay. Now, Abhishek, I just forgot. In an array, the left child is A to I, right? So for the left skew tree, the space will be 2. Okay. I'm sorry. You have more space, right? Order of n square. What you are trying to say? Yes. Okay. Okay. Let me go for the next topic. Soumya, you just wanted me to draw a BST for 33224. Okay. Can I draw this at the end? Because people might get confused. So at the break time, I'll draw and show you. Okay? Yeah. Please remind me. So I have to answer 2 questions. One is something about why in order is not possible for the last example and this one. 2 I'll do. Don't worry. Okay. So I'm just quickly going. This you would have seen with my own example. So I'm just going to the next slide. So finding is also order of n. So I think you are okay with it. That's what I told you now, Amit. Amit has a big valid question. Let's say the Soumya's question. Let's say I've got 3, 3 as my element. So let me start answering that because a lot of people. Now when I have to design a binary search tree, let's say I said the first element is always root element. Okay, your pencil should be activated. So first element is 3. Okay, got it. Next, as per Soumya's request or Amal, there is one more element called 3. Should I put in the left side or right side? This will be a lot of people have a question. I told you that's what you should make up your mind whether you'll put on the left subtree or right subtree. As I told you, left subtree. So put it on the left subtree. Got it? No, someone said, can't you put on right? But make sure that whole tree has that rule applied. Now next two elements were 2, 2. Okay? So 2 is smaller than 3. So again, left side. Again 2 is smaller, left side. Got it? So this is what you are going to end up if you are considering the left case. If someone said no, right case, 3 right side, 2 smaller, okay, 2 again small greater. So you get again this is also a skew tree. This is also a skew tree. This is also called a zigzag skew tree. Okay? No. This is the correct answer here. This, if we are saying left, sorry. This we are saying if it is left side. Okay? This I told if it is a right. Okay? If you say equal elements to put on the right side. Got it? These are the two cases. So let me clear this for a minute and we'll go. Just I think people got confused with the second case, right? But there is an error. Let me just once escape and just let me clear these here. Okay, so I think I was clear with the example where you take all the equal elements to the left side, then you got the left cube. With example 3, 3, 2, 2. And if you want to add 4, 4 will be on the right side of the 3, which is at the root node. Okay, so let that be a question at for the end. Let me go to the next topic. Okay. Yes, 13 can be on the right side of 10 here. So let me quickly go to the two new topics, that is predecessor and successor when you are doing in-order travel system. One second. What there was a number? Sir, how much to calculate how many BST possible for a given sorted list? See, for a given sorted list, you will have always only a unique BST because the condition is imposed here. Without condition, if you talk about binary trees, you can have 2 power n of those trees. How to solve the problem like in order and pre-order, post order need to be find it. Follow me this, I think we can discuss little bit later. Let's try to just finish the topics and we'll go to that. Right. Sorry, I'm not ignoring your questions, but I just want to finish certain topics today. Then we'll introduce those questions also. Okay. Now we introduce two concepts, that is in order when you're doing an in order travel tree, which node is called as a predecessor and successor for a particular node. Why do you use a predecessor successor? Always to find out the maximum element in a subtree or a minimum element in a subtree. To do these two things, we just try to find a predecessor and successor. Okay. For example, let's have a look at this following tree. Would you call this as a binary search tree or no? I have not given values, but this is no, I am not given values on the road, but assume that they are satisfying. They are satisfying the condition. Physically, because what Anirudh said is valid, because there are no values, how can you say it as a BST or not? But assume that the values were satisfying, imagine that that's a satisfying BST. Now, when you find, let's say there is an element called X. Now, if you have to find its predecessor and successor of the element X itself, this X has got left subtree and it has got right subtree. Yes, I hope this has got, and it from X, if you clearly see, it is a full binary tree and also binary search tree. Now, in those cases, what you do is the left child. In the left child, the rightmost element, which means the element with maximum value is the predecessor. Okay, in the left rightmost child, okay, is called as the predecessor, and in the right subtree, okay, once again, okay, I want to find a predecessor of this X. Okay, how do I do? Now this X has got left chain and right chain. Do you agree? Left subtree and right subtree. It has got both right subtree and left. This is left subtree and this is right subtree, right? In the left subtree, when you are traveling, the rightmost element, this is the rightmost. If you still have tree, then you'll still travel. Okay, the rightmost element is called as predecessor. Okay, see, left subtree and the minimum value. That's what I said here. The minimum value will come out. Okay, so this will be the maximum value of the X. Whatever you find the maximum value of X is called as predecessor, and successor is the minimum value in the right subtree is called as a successor of node X. Is that clear or no? Just I want to get the clarity. If no, I'll just once again. Okay, let me go back. See, for an X, when you are finding the maximum value in its left subtree, maximum value in its left subtree is called as predecessor. Okay, predecessor. Maximum value in left subtree is called predecessor. The minimum value in its right subtree is called as a successor. Got this now? Maximum value in left subtree, when you find that particular value of that X node is called as a predecessor, because we do always an in-order traversal, and whenever this is assuming the traversal is done as in-order, and whenever you find the minimum value in the right subtree, you call it as successor. That's one thing. Now, why do I use predecessor and successor is to find the maximum and minimum elements when we are doing in-order traversal. There is a function called predecessor and successor. That's what I'll just talk about. Successor is this one. For this, see, the successor is there. The right chain you have, no, this becomes the successor. Okay. No, there is no pre-order and post-order, predecessor or successor. Only predecessor and successor are there for in order only. Okay, there is no pre-order predecessor or no in order. Post-order predecessors or successor. It is only when you are doing in order you can use the predecessor and successor. Okay. Now let me finish the slide. If the right chain, right node is on, then you will say that the successor is absent. The successor is absent. Okay. There is no successor for node X. But predecessor should be there because that node exists. I should have an ancestor to arrive, but there is no necessary that there should be next generation from it. So the successor may exist, may not exist, but predecessor 100% exists. Okay, got it? Right? Success. If let's say you are a node, let's say, and you doesn't have any chain nodes, neither left chain and neither right chain. You cannot find the successor because successor is after the node X is the next path. Right? For predecessor, what I say is, predecessor, since I have reached somewhere else, I can have an ancestor. How do I find the ancestor is? Let me finish for a minute here, then you will have those valid questions. Okay. See, what I say is, if I do not have a left chain, it is assumed that the predecessors cannot be found. But when I do an in order, where do I start? From where do I start in order here? Let's say for this tree, from where do I start? The leftmost, right? See, if I start the first leftmost element, what I get is the predecessor. That's why in order only I can do the predecessor. Somewhere I start. Even if it is a left skew tree, I'll start from somewhere else, right? And this is not imposed mostly on the skew tree concepts. Got it? That's why we say predecessor exists. Okay, now we have it. If there is no left chain for a node, then the same node is the predecessor. Yes, sometimes, but that is a very rare case, Chinmay, where you will say the tree is a skew tree. That's why successor and predecessor cannot be formed. Got it? So that's a problem when you have the skew trees. There is no left chain at all. Predecessor, yes, you can call that as a predecessor because when you have the right skew tree, the first root node itself is the left. So that's why you can call it. Okay. figure 1, this one. So what I'm trying to do is I'm trying to find the predecessor for x and successor for x. So what is that? The x, for an x, the predecessor will be the largest value in its left tree and the successor will be the smallest value in its right subtree. If a tree has only root, if a tree has only root, we will not say it because root element. It's just a root element, right? It has not got, so we ignore saying that this tree will have a predecessor and successor. Okay. You asked about first one. Okay, sorry, figure one, right? I'm sorry. Okay. So there is a question. Now what it says is, let's say I have to find the predecessor for node X. Unfortunately, there is no left subtree. Okay, there is no left. In those cases, what I do is the first left subtree's ancestor is called as the predecessor of X. Okay, that is what we have discussed. Okay. Now let me go for inserting an element and deletion of an element. So insertion and deletion I will do little quickly. So after insertion and deletion we will have a break, and at that time questions will be asked. You can ask me the questions, right? Can I just try to finish the insertion of element? Okay. See, insertion is the simplest task or easiest task which can be performed by binary search tree, and the time complexity is order of n. Right? That order of n is a worst case scenario. Why? Because we are assuming the tree can be a left skew tree or right skew tree. Okay, if it is a balanced tree, then it can be order of log n only. Okay, so let's first try to understand how I will do. Let's say if you have to insert element 5, the process always starts from top to bottom. Why top to bottom? I will try to compare first where does the element fit in, either the left subtree or the right subtree. So first I check for the root. If there exists a root node, the next step I do is check for the value associated, whether it is going to travel on the right side or the left side. So the root value is 6 and the inserted value should be 5. So 5 is smaller than 6, so should I travel to the left subtree? One clarity is gone. So do I am traveling the whole tree? No. So half of the tree transfer has been reduced. So that is a case when the tree is not skewed. If the tree is skewed, still the time complexity is order of n. That's why I told you worst case is order of n, assuming the tree can be a skew tree. Right? If it is not a skew tree, the average case is order of log n. Do you agree with me that now in a binary search tree, why these time complexity are varying? Where I'm assuming it to be order of n, order of log n, but still present I saying order of log n. You got that? Why it is n difference? Why it is n? Why not log n? The reason is the skew tree conditions are still there, and this we overcome with something called as balanced binary factor. Okay, let me just quickly finish the insertion. So you compare the value to the root, you decide to the left, and the same process is repeated until you find a null location. For example, after 2 I realize the 5 is greater, I should travel to the right side. So once I travel to the right, I have another child element where I compare its value, okay, and then I try to insert. After 4 there is null, but I insert to the right side null. Okay, got that? Now let's take 4 is absent. Where should be 5 inserted now? Let's assume 4 is absent. Where will you insert 5? No, let's on the place of the 4. Yes, in place of. Why? Because after 2, you decide there should be a right tree, and there would be no right tree. So simply the right pointer will be the 5 is greater than 2, so it should travel right, and right pointer child node was done, so you replace that null with the new value. Okay. Now, so 5 is greater than 4, right, Suchitra? So that's why I kept it on the right side of the 4. Now 5 is less than 6, that's why it is on the left side. Okay, got it? Sorry, there is a correction. This is the wrong BST. Why? Because 3 should not be here, 3 should have been somewhere on the right side. Got it? I'm sorry, I did not notice that. Thanks for correcting me. This 3 is technically wrong. Okay, so let me correct that right here. So this is present at a wrong position. Okay, sorry. So just assume that 3 is absent. Now we are clear. If not, 3 would be here, 4 and then 5. Got it? Okay. Q3, the tree which is only traveling towards left or only traveling towards right, not both left and right, is called as a Q3. Okay? Okay. Okay. You wanted me to mark this as to 0. Okay. It's not 3, it's 0. Okay, then it is correct. Okay, if it is 3, it is correct. If it is, if it is 0, it's correct. If it is 3, it's wrong. No, I marked it to 0, so it's a valid BST. Thanks Karan for helping me with 0. Right, now deletion of element. So I'll quickly finish deletion, or do you want to have a break? If you want to have a break, that's fine. If you want me to finish, okay, I'll finish deletion because I don't want to discuss. Okay, now I have a question. First, let me ask the question. Every node, how many child it can have at max? A node, how many child it can have at max? 2. Minimum? Average? 1. Okay. 0, 1, 2. A node can have either 0 child or 1 child or 2. All are correct. Now when I'm deleting a node, what are the 3 conditions that you can find? What are the 3 conditions that you can find when I'm deleting a node? A node with 0 child, a node with 1 child, a node with 2 child. Okay, out of these 3, which is the easiest one do you feel to delete a node? A node without a child, right? Got it. Now let's say if I have to delete 5, do I have to do any work here? Do I have to do any work here? No. Simply I'll pointer to right child to null. Is that easy? Is that easy? Yes, that's the one case of a deletion. Now let's go to the next case which has got 1 child. Now 2 has got how many chains here? It has got 1 and 4. But the deletion element is 4, so you should concentrate on the chains of the deletion element. So 4 is to be deleted. How many chains it has? It has got only 1 chain. Now what should I do? If I delete 4, there will be a connection missing from 2 to 3. How was the connection between 2 to 3 currently? 2, 4, 3, right? If I'm deleting 4, I'll also deleting 3 connection, which should not happen, right? Do you agree that or no? Should not happen, right? 3, yeah, because 3 is the subtree of 2. So what I do in those cases, first of all, I try to point 2's child instead of 4, I'll try to point 2 to 3 and 3 I'll just delete. There will be, I'll discard the connection. First step is always point the child to the ancestral node, which is parent of 4 or parent of the deleted node, and delete the node. This is how you can delete when you have got 1 chain. No, that's the next case. If 4 has got 2 chains, that's a different question. If 4 has got 2 chains, that's the third case. BK, you have a question, just please post it. Let me finish the last case, that is if 4 has got 2 chains. In that case, I am taking an example, 8 getting 2 chains. Okay. Now, okay, you want me to explain the one case again? Okay, great. So I'm explaining, let's say there is a node to be deleted, which is 4. Okay. Now, if I have to delete 4, can I delete it directly as I have deleted in the previous case 5? Do you agree with that? Can I delete 4 directly as I have deleted 5? Why no? Because 4 has a chain called 3 and I don't want to delete 4 and 3. I just want to delete only the node 4. Yes? Now 4 has got 1 chain and this chain is part of the BST. Yes? Rebuilding is happening. Technically, the way I am saying is a rebuilding of the tree. Rebuilding of tree. When you are inserting a new element, rebuilding of tree is not necessary. Why? Because there is no balancing factor. When balancing factor comes, rebuilding is necessary. But now we are not worrying about rebuilding for insertion. Why? Because that's it. BST, satisfied BST. But deleting, rebuilding is what I am considering. I should have not. 1 second. Yeah. Okay. So let's talk about the 1 node deletion and 2 nodes, and then we'll go for a break. See, when you're deleting a node 4, it's only node 4 to be deleted, not its children or its subtree. In that case, what I do is first I'll see how many chains are there. There is only 1 chain. So what I can do is the chain first will be mapped to 2. Which means 2's right child is no more 4, it is the 3, and then I will delete the 4. That's simple way when you have 0 and 1. The question raises when its node to be deleted has got 2 childs. Now let's take, I have to delete 8. How many childs 8 has got? 2. Yes, so 3 will be marked as the second child to will be marked as child to 2 and 4 will be. That's what we do. Now let's say 8 has to be deleted. How many childs does 8 has? 2. Now if I delete 8, what will happen here? If I delete 8 directly without will happen, I will miss complete subtree of the 8. Yes or no? Do I miss? If I delete 8 node directly, I will be also missing the complete subtree 5978. Now there is a solution. This solution can be ambiguous with the video lectures, but I'll give you both the answers first. Either first solution. Replace the element with the largest element in its left subtree. That's one solution. Or else, replace the smallest element in its right subtree. Both are valid solutions. Why? Can anyone explain me why? See, first of all, let me repeat the solution. The first step is replace the element to be deleted with the largest element in its left subtree. That's one solution. Or smallest element in its right subtree. When you read the recording lecture, it says smallest element in the right subtree. Both will give you here, don't worry. Why? Because in the root node, if you have the smallest from the right, all the elements will be larger than that element. If you are taking the largest element from the left, all the smallest elements are there. Okay? Yeah, both predecessor or successor, whatever you want to take. Yes. Okay, now that's the reason. Now first step is I will find the largest element in my left subtree. Replace. See, I'm not deleting it. I'm just copying 7 to 8's value. So 8 is just replaced with 7 and 7 will be deleted in the process of deletion of one single where 5 will be linked to 6 and 7 will be deleted. This is the way how the deletion will happen. Now before going to the break, I'll just talk about something called balancing factor. Now the problem that we have seen with the insertion and searching was order of n because of occurrence of something called as Q-tips. To avoid this, we introduce a concept called balancing factor. What is balancing? When you do left subtree minus right subtree, always the node should end up with 0 as value. If this is occurs, we get order of log n. Topic called AVL that I'll discuss after the break. So we'll take 5 minutes break. AVL, I hope you have enjoyed till now. Till now you have enjoyed the concept. AVL will be more interesting and you will be little confused, but all your confusions will be clear, and then we will do some examples. Right? Great. Do not worry, I will be not rushing for this concept of AVL because we have certain important topics from AVL. See, AVL and heap sort are part of the exam. Do not worry. Do I need to learn quick sort, bubble sort? These no. You will be only learning one sorting, that is heap sort, and which will be covered in the next class or next to next class, depending upon how much we covered today. Okay. I will also revamp the syllabus because there is little ambiguous with people, so I will give you clear syllabus. I'll remove the topics that you should not focus by highlighting it or completely I'll remove, and I'll also map them with the CLR textbook because handout is mapped to the Godman book, right? And I'll upload it by Monday evening, and that's a word, and I'm not going to break this. Okay. So let me first stop this, and then we will go for a break, and then we will discuss. I can do it. So one of your friend has the following question. He said, if we are taking the case of the largest in the left side, instead of that, let's take the smallest on the right. For this example, if I take the smallest, 8 will be simply replaced with 9 here. That's what. Instead of 7, you can replace with 9. The condition is you are taking the smallest element in the right side. Yes, you can do SSM. Sorry, someone wrote SSM. I read that. Yes, you can do. The condition what you are imposing is the smallest element in the right subtree. But okay, for a balanced BST, the difference between left subtree, no, balance is always 0. Okay, if you are saying the difference between left subtree and right subtree is okay, there is one more question from Lakshmesh. He saying the balanced binary tree, the height difference between left and right subtree should be 1. No, that concept is called as AVL. In binary trees, if we say balancing, it is 0. Okay, so I'll just drink water and we'll continue with AVLK. Akash, you have some question. You said successor may or may not be there, but predecessor has to be there. What if left subtree is not? We go to ancestor. Please explain. Okay, Akash, you have a valid question. Now what happens is, let's say I have got right skew trio, right skew. Now when I say, let's say I have to find a predecessor for, let's say, node X, which is just leave but one node. Okay. Now if in order where I start, I try to start from the leftmost node. I don't have left tree. Now the first is left root right. In order transfer is that. So the root I'll address. So that root becomes my, the first left ancestor is the root. That's why it becomes my predecessor. Got it? So there is what. Swastik, I just missed your question. Just 1 second here. Swastik, replace 8 with 7. Okay. Swastik, please. Please just do not post question for a minute because I'm missing one of the questions from Swastik. Swastik has question. Replace 8 with 7. Okay, I'm going back. Replace 8 with 7. Where is the node 6 will be replaced? Good. Swastik, let's look at this. If I'm just replacing 7, which is 7 is existing, I'm copying 7 to 8. So 7 is existing. Now if you see this case, which element I should delete? I should delete 7th element, right? I have to delete 7th element. To delete, when you look, 7 has got only one change, so I will put the link between 5 to 6 and then I will delete 7. Got it, Swastik? See, 7 is copied at 8th place, 7 is copied at 8th place, and 7 exists here. Now I have my deletion node is 7. 8 is replaced, there is no more. So 7 deletion, if you see it has got one chain, I will use the concept of one chain deletion. Got it? And that I will do here. Okay. Naveen, you were having a question. Can you please pose the question? One second. What should be the input? See, the node that has to be deleted should be the input parameter following, not the other node. So here what happens is when deletion is happening, the restructuring of BST is always checked and they do that. Okay, there are functions. Where will 6 be in left subtree or no? 6 will be in the left subtree over here. Okay, because 6 is smaller than 7, so 6 should be on the left subtree. Got it? So just can you give me 5 minutes break here? I'll just drink water and come. Yes, 6 will be placed on the right side of the, so basically we will say on the right chain. Yes. Yeah. No, see when I'm talking as right chain, left subtree. 8 ke paas hai na, so this is all my subtree as the right child of 5 nodes. Yes, you are correct, Sumit. As the right child of node 5. Okay, so just I'm stopping the recording for a minute and I'll just drink water and we'll continue with AVA. Okay. Right. So there was an issue when we were doing the binary search tree, especially we were encountering most of order of n as the worst case because of the skew tree. To overcome this problem, what we decided is let's put a balancing factor. What does a balancing factor means is when I do the subtraction of the left tree, height of the left tree minus right subtree, I'll get all the height of the left subtree minus right subtree. The node should always end up with 0 as a balancing factor. Matlab it should have 2 left subchains, then it should have the 2 right subchains. So that is what we are trying to say. But this is not feasible because always we cannot expect a tree to be a full binary tree. Okay, full binary tree. For example, if you take this tree as an example, the height difference at 8 is 0 because the left chain, the height of the left is 2, right is 2. But when I take the height of the node 6, the left child is 1 and right child is 0. The height factor of 6 is not giving me 0, but it is giving me 1. So this is the kind of problem if we encounter when we say height balancing factor should be equal to 0. To overcome this problem, what they said is let's put some relaxation on a binary search tree. It should be a binary search tree. And the height difference between the left subtree and right subtree can be maximum 1. If it is there, always our search operation will be in the best case worst case also will be order of log n. Okay, why we are imposing the balance factoring condition is to ensure that the search in operation or insertion operation always happen in the worst case, even in the worst case should happen in log n time. Got that? So that is what, if that condition is imposed, the height balancing factor condition is imposed on a binary search tree with 1, then that tree is called as an AVL tree. And AVL tree performances are done especially when you are doing the load balancing factors. Okay, load balancing factor if you have got multi-process system. That's the way how your load is going to be distributed. Okay, Bapu, that's the real-time example of an AVL tree. Load balancing factors are a simple, all your load balancing algorithms work on a binary tree with this balancing factor. Okay, that's and AVL has a full form which is Ederson, Whiskey, Landison. These are the 3 scientists. Oh, I did not start. Guys, you did not told I was in mute. Sorry, I have to restart. Okay, so I got it. Now I was in mute here. I'm sorry, I did not notice it. Thanks for reminding. Okay, okay. Let me restart it. Let me restart it once again, which I missed. Sorry. Let me go back. See, I'll just restart with the balancing factor, and I'll talk about AVL once again. So what happens is, since to avoid the time complexity of a binary search tree to order of n, to make it always order of log n, which is the worst case also they wanted to perform the search operation order of log n, they decided to impose something called as balancing factor. The imposition of balancing factor in binary search tree, they said the difference between the left and right always should be 0. And this is not feasible in most of the tree conditions. For example, if you take the figure 2, what happens is, this is a binary search tree. Okay, this is a binary search tree. Okay, and if you see the balancing factor of 8, it has got 2 left chain. It has got 2 left. The height of the left is 2, and the height of the right subtree is 2. When you do the balancing factor left, say why this is automatically changing. Sorry, just for a minute. Okay. Okay. When this is done, I am satisfying the balancing factoring at node 8 because 2 minus 2 is equal to 0. When I am coming to the subchain, that's the left subtree, the height balancing factor between the node 6 is giving 1 minus 0 to be 1. And even with these kind, we can try to make sure that the time complexity is coming to be order of log. And when we try to impose the height balancing factor, the difference between the left subtree and right subtree to be 1, then we call that binary search tree to be an AVL tree. And AVL stands for the scientist who has improved the binary search tree such that the operations are performed in order of log n with a height balancing factor such that the difference between left and right should be at max by 1. Okay. Now I think Arun, how it is 1? Okay. How many nodes the 6 has? How many left child the 6 has? 1. How many right child it has? Right. 6. So 1 minus 6 is 1. So that's why 6 has got the balance factor 1. Got it? Okay. The figure 1, if you see, is not at all, the figure 1, if you see, is not at all an AVL tree. Why? Because see the height difference. At 12, the left side is 2. Let's say Yes, only an AVL tree. See, AVL trees, subtrees are always BST. A BST is only converted into an AVL tree. And that is also done with only 3 nodes at a time. That I'll explain you after a minute, so just bear for a few minutes. So if you take the figure 1, what is the height difference between, what is the height difference at root node 8? This is an AVL tree. What is the difference of height at height balancing difference at root node node 12? Node 12. So, right, node 12. Left is 2, right is 0. 2 minus 0 is 2. And that's why this is not an AVL tree. The difference at, and what is the height difference at 10? 1. So this is an AVL, but because at one point this is not satisfying, I cannot call an AVL, but this tree can be converted into AVL with something called as rotation. A non-AVL tree, a BST can be converted into AVL tree when it is dissatisfying the condition. Can you say this figure 1 as an BST first? I'll repeat here. Can you say figure 1 as BST first? Binary search tree, figure 1. Yes, it's a binary search. Can you call this figure as an AVL tree? No. Why? Because at the node 12, the height balancing between its left child and right child is more than 1, which is 2. Because left I have got 2, right I have got 0. 2 minus 0 is 2. That's why the height balancing here is 2, and which is not an AVL, which is only this is only BST, but an AVL, a BST where AVL property is mismatching can be converted into AVL. Okay, AVL, but if it's more than 1, then yes, you cannot call AVL here. Okay. Now we will introduce a topic called rotations. All the nodes of BST should maintain, yes, all the nodes of BST should maintain AVL tree property. Then only you call it as. Now let me talk. The figure 1. I'll just ask certain questions with respect to figure 1. Try to answer that. Okay. Where is the AVL property missing at figure 1? At which node the AVL property is 12. Okay. If I introduce a mechanism such that if I can make the 12 node 8, why do you feel 8 here? Gayatri, why do you feel 8 is the mechanism you are missing? What is the how many left sub 3 is? Okay, why it is not missing at 6? Why it is only missing at 12? Okay, great. I'll just use pencil at this point. I think that will help me more. Okay. Okay. How many left and right child do 9 has? Each step I'll finish. How many left and right child do 9 has? 0 left, 0 right. Difference between left and right is the height balancing. So what is the height 9 has got now? Can anyone say me? Balancing factor. 0. Okay, you agree? See, I'll write the number of chains in bracket. 9 has got 0 chain and it has got 0 right chain, right? When I do 0 minus 0, what is the height balance difference at 9? 0. Is this clear? Is this balanced? Got it. Now, let's go to 10. How many left child does 10 has got? 1. How many right child 10 has got? 0. Okay. Do the difference between 1 minus 0, it is 1. So this height difference is 1. Okay. And it is an AVL tree. Right? 9 is also AVL tree because maximum 0 or 1. Right? Okay. Now go to 12. How many left child it has got? 2. How many right child it has got? 0. What is the height balance? 2 minus 0 is what? Is 2. So this is not an AVL. Got that? Got that? Why? Now do the same thing with 3. 0, 0. So 3 is AVL. What about 6? It's 1 minus 0. Do you want me to write them? Okay, for your easy understanding, I'll write. So that next you'll know that. 0, 0 at 3. You agree? Now let's write what is the height difference at 6. I have got 1 left chain. I have got 0 right chain. 1, 0. Now I do difference 1 minus 0 is 1. This still here it's AVL. Do you agree with that? No. Highest difference. See, even I'm saying why it is not. Why at each node? Someone had asked me, sir, I feel 6 is not also. Not at every 3 steps you can do this. Okay. So what you said is height difference of the tree? No, not height difference. Sometimes at node also it acts. Why? Because I'll say you. Sorry यार, आपका नाम थोड़ा मुश्किल है मुझे pronounce करने. There is a very interesting question. Your friend say height differs from the root. Not necessarily. I'll always consider from root. Why? Because every subtree can be considered as an independent tree for understanding. Got it? -1, 1, 0 are considered as 1. Don't worry. But -1, you can write -1. It is appreciated, but still the difference is considered as 1. Don't worry. -1, 0, and 1 are all valid. You have a good question here. Now, why -1? You will understand at the deletion of this node. So don't worry. So for a minute, assume that 0, 1, -1 all are valid to be an AVL tree. Right? Now, if you see at 8, can you say anyone? Yes. For considering AVL tree, -1, 0, 1 all are considered. No positive, negative value at an instant. Okay? It is also called red-black tree. Yes, the red-black tree is the next extension here. So I will not introduce red-black tree yet. That will take whole 2 lectures to explain. The red-black tree is not part of our syllabus, and I'm not touching it also, right? And that especially with this technology, where my iPad has been not allowed to project. Otherwise, writing I could do much. AVL tree is better than red-black tree. Red-black tree is in a different scenario. Okay. Now, what is the height difference at 8? Now you say 8 ka aap batao. Got it? No, I think you got it. Why the only at node 12 it is missing the AVL property. Still, I cannot say it as an AVL tree. Got that? The figure 1? Okay. Now I will say, if I introduce a mechanism such that which will convert these 3 nodes into an AVL, then I can call my first, the figure 1 to be an AVL. If I introduce some mechanism such that if the 3 nodes can be converted into an AVL, definitely my whole tree is becoming an AVL tree. Yes or no? Okay. And important, when I'm introducing a mechanism, the mechanism is called as rotation. It is called as a rotation. We'll introduce 2 types of rotation, single rotation and double rotation, which I'll introduce you just in the next slide. With that rotation, a non-AVL tree can be converted into AVL tree. Remember, a tree becomes non-AVL at max with 3 nodes only. Okay. 2 minus 3 kitna hai here? Arul, 2 minus 3 is -1, which I said ignore the value, ignore the positive negative value. So it is 1 only, no? -1, 0 and 1. Fine. All 3 I consider to be AVL. Got it? So you got it? If 2, 0 is the case, that's what? At 12 it is 2, 0, no. At 12 it is 2, 0, 2 minus 0 is 2, and which is not considered. The height balance difference between left and right should not be greater than 1. Got it? So that's why the 2 is not, when you have a height balance factor as 2, okay, how 12 is 2, 0, I'm sorry. How many left child do 12 has? Ajay, sorry, how many left child it has? That's why I wrote 2, 0. Got it? Okay, yeah, okay. Akshay, 8 nodes. How many child nodes does 8 has? Left child node. Just talk me about left child. No need to check because already you have found it not to be an AVL, then you don't need to go to root, but let's check. 2. How many right chains you have got? Left chain, 2, 3. What is the difference at root node? -1, which is also considered to be 1. So I'm removing the sign integer. Sign integer, ignore for a minute. So it is 1. The difference is 1 because someone can say right minus left is that. Chains, the number of chains at levels. Levels is fine, but chains you have to check. Okay. If you check the level, what will happen is again 2 level minus 3 level. Still you will have the same thing. Okay. I made it chain. I'm sorry. It is the levels. Levels here. Correct. It's not chain. I should use the word level. Sorry. Please correct me. It is the level. Okay. Got it? So, right. Let me go to the next. Right. I'm sorry. Okay. So the two rotations that help me out making a non-avial tree to be an avial. Remember, a tree becomes non-avial only at max with the three nodes here. For example, let me talk. Now look at this. Let's assume that you have got a tree with AB. Will you call that tree as an valid avial tree? Okay, let me draw that also for you. I have got element A. I have got right child B. Will you call this diagram as an avial tree? This AB. Yes. Okay. Now I want to introduce a new node called C. I have introduced a new node called C. After introduction of the new node C, do you call this as an avial tree? No. Okay. Now where was the tree? Where was the new node inserted? Where was the new node inserted? Right side or left side? Use the terms right or left. It was inserted on the right subtree, okay, on the right side, right? It is RR. If you see right side of the right subtree, yes, right side of the right subtree, you can say it as R. Now, if I have to make it an avial tree, I introduce something called a single rotation called as left rotation. What is this rotation? Now, to make this tree into A and B as the root and C as the right child, will it be an avial tree? But before this, I have a question. Where was the avial property missing? C. Is the avial property missing at the node C? Is it missing at node B? Node B. B nowhere because the difference is 1. The level of the right is 1 and left is 0. It is missing. So from here my rotation starts. So from the node where the avial property is missing, from there you do the left rotation. Move the A to 1, 2, 3 for your easy understanding. So I'll try to rotate A to the left side, B to the root position and C to the right position. This is called a simply left rotation. Have you understood this or not? So just assume this is the right skew tree. You simply you tried the root to the left and suddenly it became a balanced tree. Now you got it. So now this I know. If B has left child, that I have taken care. Let me first finish the first 4 rules and then we will go to the conditions where B having a right child. That conditions we will talk. Okay. Even that case also, that's a different case called left right. It's called right left rotation. So that we'll do. No, C node is not rotated. So that's what then we call it as right rotation. Okay. So let's talk about the next kind. Now let's take this example. Okay. AB is already existing tree. Okay. Should you want me to draw the AB first? Okay. Let's say already I have got a left skew tree with A and B. Do you call this as an avial tree? Yes, you call, not SA. It's an avial tree. A and B. A and B. Array, why no? Who are saying no? I want them to answer. Okay. A and B, let's take A and B as an avial tree. When I add the new node C, is this the diagram which you see is an avial tree now? 1, 0, 1 minus 0 is 1, it's an avial tree here. AB is an avial tree. This is not an avial tree. Where was the insertion done? Where was the insertion? On the left subtree, left side of the left subtree, LL. When your insertion is done with LL concept, that's left side of left, you can do a rotation called right rotation. Right rotation. What does right rotation do? Simply make B to the root node, A to the right child, and C to be the left child. Yes, all avial trees should be a BST. That is the first and foremost condition. An avial tree is a superset of BST. Okay. Now let's have a look. Let's say these are the values. Do you call this as an AVL tree now? Alright, I remember if B has a left child, what to do. And let me finish the concept first, then I'll take those scenarios which you have in your mind. How come left has become greater here? But now left is greater than right value. How? See, A's value is 3, B's value is 2, C's value is 1. How did it become? That's why it kept the values next to them here. So the inserted value was 1. So if you see, if you do the rotation, right side I've got 3 only, no? Raghavan, is it clear or you have a question? See Raghavan, let's say A, B, C. C was the introduced value. So it became a left skew tree. To make it an AVL tree, I did the right rotation. When I did the right rotation, A was sent to the right side. B was at root and C was at left side. And the values associated to them is, see, left side I've got 1, root I've got 2, and A I've got 3. And it's a BST also. All BST, an AVL tree should be an BST first, then an AVL. Now it's clear, right rotation is clear. Can I move to the next conditions? Okay, that's why I wrote the values next to them here. Yes, the maximum height of a AVL tree should be only 1, 0 or 1. Okay, yeah. Now let me go to the some condition where I might not encounter right skew tree or left skew tree. Can I have insertion like this? Let's say I have got A, I have got B. Can we see inserted on the right side? Let's say A first node, B left node. Okay, C can be right side of the B. Can be there a situation? Yes. If that situation comes, it can. This is one of the situations. Is this valid situation where C is making the tree a non-AVL tree? Where is non-AVL happening? Remember, that's the node A. Always node A, right? Node A. From their rotations. Now, for these case, we do something called as double rotation. Double rotation. What we do is, where was the first insertion happen? The first insertion happened on the left subtree on the right. Left subtree on the right. That's why it is called left-right rotation. So left subtree on the right side it has that. Now what I do? The first rotation I do is left rotation. LR is not left right. LR stands for left rotation. Where do I do this rotation? Is A is not AVL, but this has 2 steps. Double rotation has 2 steps. Yes, AVL I have included, and that's what I told you. I'll upload here. Upload the revised syllabus because AVL is sub part of BST. So when the BST is covered, AVL should be covered, and that's why I forgot to mention. I'll add it. Don't worry. Okay. Now let's see. Now have a look. Now after insertion of C, the tree became non-AVL, right? After insertion of C, the tree became non-AVL. Now what you should do is, first you should do left rotation, not on the A node, on the B node. Here AVL property is missing. B has an AVL, but still your rotation should be done to the B. Now what rotation? Pushing C to B's position and B's to the left side. Got it? This is the first step. Yes, double rotation was needed because of C. C node is an AVL, but because of insertion of C node, A node became non-AVL. So that's what. So A node, the node that became non-AVL, its first chain should be rotated. This left-right rotation. Next rotation. Only one rotation. Is still it an AVL? Can you say this? The new diagram is an AVL? No. What should I do to make it an AVL? Which rotation would you suggest me to do? Right rotation. Do a right rotation. Right? That's what. It made me an AVL. Can you see this clear? Yes, we are also shifting. Yes, you are correct. Yes, that's why we are doing 2 operations. First operation we did is when the insertion happened on the left side, on the right side of the left subtree, we do first left rotation on the inserted value and its parent, not at the node where AVL property missed. After that, we do the right rotation on the node where the AVL property missed. You got it? This is called as AVL. Cost involvement, Khan, I forgot. I'll just recollect and let you know by end or in the next session here. Conversion cost, I really have forgotten it here. Now got the concept of left-right rotation? First do the left rotation on the node that is inserted and the parent node of the inserted node, and then do the right rotation on the root node where AVL is being missing. Can you please explain how AVL property is missing at node C? No, see, node C is not missing an AVL property here. Do you want me to explain node C AVL property here? How it is missing? It doesn't have any left or right chain. So the balancing factor at C is 0. The missing of AVL property is happening at A. At here it is happening. But still I had the missing of A had happened because of C. I start the left rotation on C. No, it won't break here. A and C, direct connection became indirect connection. It became indirect. A to C, C to B. There is no connection breaking. We do recursion. Yes, Khan, you can email me, not issue. Yes, Shivam, the double rotation is mandate when you have insertion on the right side of a left subtree or left side of a right subtree. Okay, let me go to the next. We will see this with an example. See, to make it into the format of a right rotation or left rotation, that's really a little ambiguous question, Shreya. I have to really think on that here. You had a valid question. Why not do right first and then left rotation? Technically, when you do, that becomes an imbalanced BST. Okay. Okay. Let me do the right rotation first. Right left rotation next. Okay. Okay. Lamba, you have a. Let's finish this. Then I'll address all your questions here. Okay. Now let's have the right left rotation for a minute. When do I do a right left rotation? Is in the right subtree if my insertion is happening on the left side. What will be the first rotation I'll do here? Will I do the right rotation here or the left rotation here? The name itself says first do the right rotation, then do the left rotation. Now when I'm doing right rotation, I'll do right rotation only to the node that is being inserted. So C, I will be doing right rotation, which means C will take over the place of B and B will be pushed to the right side. So you can see 3, 4, 5. So the rotation has happened between C to B. This is the first. The next what I will do, since if you see the imbalance is still continuing at root node A, I have root node, the node A, still I have to do left rotation. Once I do the left rotation, my tree becomes an AVL. I hope little ambiguous was there with the right left rotation and left right rotation. Let's look at them with example. Can I go for an example or you're clear? Yeah, okay. Now you will have a lot of questions minding because Prasanna just took a simple left skew tree or right skew tree where he was missing a lot of children, but I can have a lot of childs, but I will, how he took a simple example and he's trying to explain me easily. Let's go with all the kind of questions what is going on in your brain. Okay. Let's try first, I will only make the concept simple. I'll not take right rotation, I'll do left rotation. You have to do right rotation for me. Okay, so let's take an example. Is this an AVL tree? First of all, first say me this is an AVL tree. Why no? Why no? It is not satisfying the AVL balancing property at node A, correct? A balancing factor at node. Now, this is not left skew tree. First of all, look at that. Is it the left skew tree? Is it a left skew tree? No, no, it's a left skew tree. Shivam, why? Because I say A has a right chain. I did not mention AR stands for A's right chain, BR stands for B's right chain, CR stands for, sorry, I have to put C, here there is a spell mistake, let me correct it right now. This is CL and this is CR. Okay, correction done? Yeah, okay. Now when I have to do the rotation, which rotation would you suggest here? Right rotation or left rotation? Right rotation. Perfect. You are saying you want me to do. Now when I do right rotation, what is the effect that now I have subchains? Do I have children to C node I have children, for B node I have a child, for A node I have a child, right? Yes or no? Now how to handle these kind of situations? See, remember, whenever you are doing rotation, you are only doing on 3 nodes. Only doing on 3 nodes. What are those 3 nodes? Is A, B, C. Yes? Because if you see what I have thought is with example of A, B, C. Just take those A, B, C for instance. Just take those A, B, C. Do the rotation for A, B, C only. What will be your outcome? This BCA, just forget CBA. Just focus till this point here. Is that clear? Till this point it is clear? CBA is clear. Now I have to handle with the child nodes. See, the child nodes. There are total 4 child nodes I have to handle. Right. Now where is the child node of A? On which side child node of A is there? Child node of A is on the right side. Just keep that on the right side of node A. Is that clear? Keep the right side on node A. Okay. What are the child nodes that C is carrying? Child nodes that C is carrying. This node here, this A's right node is on the A's right side only. See here. Okay. Now C has got 2 child nodes. It is carrying with them. Now which child node is missing? B's child node. Yeah. Now what should do? Which side is the B child node? Yeah. Of B. Which side is the B child node? No, from B. From B. Where is the B's child node? Is it on right side? Right. Now where is the new position of B? Where is the new position of B? Root. Now where should be its child also? Where should be its child also? Right side. No, it should be right side. First right side. When I go to right side, do I have an empty position? Do I have an empty position? No. So to keep, where is the empty position? I got the empty position on the left side of the right side. Just place that. That's as simple as that. Okay, Lamba, you have a question? Okay, why can't B be kept as? Okay, great. Now, okay, one of your friends has a very good question. So let me, his question I'll draw, then we'll have the clarity. He says, I don't want to put BR here. Okay, he wants to put BR somewhere as the child of CR. Do you want me to put child as CR? Okay, AR. Okay. Is it a AVL tree? Pawan, is it? That's why. Got it? So when we are doing balancing factor, we try to make sure that because of our new rotations, it should not become a non-linear. Because here I can only do one rotation, no double rotation. That's why I put it here. Got that answer? Okay? Yes, this is just the right rotation. You did the rotation. Right. Okay? Why it's a right rotation, but still we call it as left rotation because the placement has happened on the left side. Okay, see here. Once again, I'm going back. Let me go back here. Oh, sorry, I typed it wrongly. It's right rotation. Sorry. It's a right rotation. I typed it left rotation. I'm sorry, here. 2 mistakes I did today. Okay, this is right rotation. Please correct this here. Okay, pen is not working. Okay, one second. Khan, you have a question? Let me. But placing BR to here in any way wrong as it violates BST. Yes, correct. It also violates BST and AVL property. I did not focus on that BST portion. Okay. Okay, you want me to have an example? Okay, great. Okay, let me go with another example. I'll just come back to that later once I finish this example here. Okay. So let's draw an AVL tree with 1, 2, 3, 6, 7. Don't worry if you have not understand today. Tomorrow I'll take one more example and solve an AVL. Don't worry. We'll focus on AVL tomorrow also. Right? Is that okay? Is that okay if I consider AVL tomorrow also? Yeah. Okay. So don't rush. If you have understood, fine. If not also, it's okay. Let's try to solve this step by step and see whether you have understood it or not. Okay, so there is a small typographic error in this example because okay. So the values, yes, correct. Here I did not have it done, but on the notes there is another example here. So let's try to build an ABL tree. What will be the root node here? Yeah, BSC also again. Is this one, with 1, 2, 3? This is the tree that you can get. The sides that I have written are their left and right child for your. Now, is it an AVL tree? The 1, 2, 3 is an AVL tree? No. What rotation would you suggest me to do over here? The left rotation, right? Okay. So let me do the left rotation. Is this an AVL tree now? This is an AVL tree. Okay. Now what is the next element that I should insert? 6. Where should I insert the 6? After the 3. The right child of 3. Is this an AVL tree? One second here. Is the screen visible now? Is this an AVL tree? Yes or no? This is an AVL tree, Shivam. Please, I'm sorry, I'm taking Shivam's name because his answer is the first to come. See, is it an AVL or no? It's an AVL tree. That's why I wrote the height balancing. 0, 0, 0, 1, 1, 2. 1 minus 2 is still. So it's an, yeah, it's an AVL. Now what is the next element I should insert? 7. Okay. I insert 7. Let me go to the next. Okay. I have inserted. Is 7 making the tree an AVL or no? Okay. Now good. That's why I asked you to use pen and paper here. Okay. Now where the AVL property is missing? Where the AVL property is missing? Now which rotation would you suggest me to do here? Which rotation would you suggest me to do here? Left rotation. If I do the left rotation, is this my tree? This is my tree? Okay. Is it an AVL tree? Okay. Now you understood how to. See, after inserting 5, there will be a small ambiguous. This I will explain in the next class. Is this okay? So what I will do is from next class, before we enter to the next class, I would like to explain you this concepts clearly, these two concepts. That is, when I have got the left chains, when I have got the right chains. Okay, I'll try to do them live in the class. Okay. So once you are clear with this, we will discuss on the problem continuation of this with value 5. No, when okay, insert 5 I'll do. For you I'll insert 5, but what rotation you will do, let me see. After 5 insertion, where did I have inserted here? Yes, you have class tomorrow. Okay, final answer is this. One second. So there was someone has requested. I did already. I have uploaded here. The PPTs will be uploaded from the Pilani campus, so I can't. Now let's say I just have one last question. Can you see the answer after insertion of 5? 2, 1, 5, 3, 6, 7. Okay. Now is the final answer an ABL or not? Please answer me right now. Now how to make this AVL we will see in the next class. That's what I'm trying to say. So to understand this, you should understand those concepts. So tomorrow we'll have this class at same time 11 to 1 o'clock. Okay. So tomorrow I'll try to explain you those two concepts, that is how to do left or right rotation when they have got children, and how to do the left right or right left rotation when there are children. Once you understand them, the example becomes pretty easy. Okay, right? I hope you are clear with the example of single left rotation, single right rotation, left right rotation, right left rotation when there are no children. Are you clear with those? Okay, fine. So with the chain notes we will discuss tomorrow. There is no red black tree as part of your syllabus. Okay, red black tree is not part of. Tomorrow we can. No need, no need. Yeah, don't attend because AVL trees are not there in your recording lectures as far as I know. Okay. What I'll do is tomorrow I'll update the syllabus. Just have a look at. I'm trying to remove all the topics that what I'm not covered except hash table. Hash table is the one that you have to self-learn to come to the rest. All you should focus on the topics that we are covering on tomorrow till today and tomorrow and the last session on 22nd or 23rd, the next Saturday session. Okay, we'll have a session on 16th, then one more session. Till if I'm able to finish heap sort by 16th, it's fine. Okay, if not, we will have to finish the heap sort on 16th. Okay? Yes, AVL is part of the mid India. Okay, on what basis do I decide left or right rotate? The type of insert. If the element is inserted on the left subtree of the left side, then I do the right rotation. Got it? Even people call them vice versa. Since I'm doing in the right rotation, someone call it as right. Okay, so let's discuss those all questions tomorrow. Heap sorting is there. Yes, heap sorting is part of this. So let me once pause this.